Hi everyone, this is Yinlam Chow from Google Research. Today I'm going to talk about the work on safe policy learning for continuous control and applications to indoor robot navigation. This is a joint work with Ofir, Nachum, Aleksandra, Faust, Mohammad, Ghavamzadeh, and Edgar, Dueñez. In this work, we study the problem of safety in sequential decision making, in which there are two notions of safety that we considered. The first is reachability, that the agent is deemed safe if it doesn't enter an undesirable region with high probability. The second is visitation to dangerous areas, in which the agent is considered safe if it doesn't stay long in undesirable regions. Utilizing these two notions, we formulate our safe reinforcement learning problems using the framework of constraint Markov decision process, in which the objective is to minimize a primary cumulative cost, where the safety constraint is posed using an expected cumulative constraint, as you see here. In this work, not only do we want our agent or policy to be safe when it is trained until convergence, we also require that to be safe during training, which makes the problem more challenging. Our algorithms are hinged on the so-called Lyapunov approach for safe reinforcement learning, which is originated by Chow et al. Back at NeurIPS 2018. This approach consists of two steps. The first is so-called safety verifications, in which, given a policy, we can check if it is safe if we can find a Lyapunov function that satisfies these three conditions. The second part is so-called safe policy search, in which, given a Lyapunov functions, we can construct the so-called safety tube constraint sets, in which in policy optimization with these constraint sets can guarantee safety. In our work, we extend the Lyapunov approach to handle continuous actions in reinforcement learning. There are two classes of algorithms that we propose. The first is the constraint policy gradient, which we formulate the previous Lyapunov approach using constraint optimization over policy parameters. This framework also incorporates standard algorithms such as CPO in this literature. The second approach is so-called embedded safety layer, which is a newer approach that we augment the policy network with this Lyapunov constraint in an end-to-end fashion. With this augmented architecture, it is quite handy that we can apply standard reinforcement learning algorithms to solve the safety problem. To demonstrate the effectiveness of these algorithms, we test the safe RL methods on a couple of domains. The first is the benchmark domains of MuJoCo, such as these half-cheater safe problem. The main objective here is to make sure the half-cheater runs smoothly and quickly, while the constraint here is to make sure the half-cheater doesn't fall down in an unstable way. So here we basically constrain its torque energy. Here are the numerical results for our Lyapunov methods when compared to a couple of baselines. You can definitely see that our Lyapunov methods in blue and green can well balance safety and the performance in terms of return maximizations, while standard baselines such as Lagrangian methods can guarantee safety during convergence, but it fails to guarantee safety during training. As you can see, it jiggles around the constraints. Here are the video demonstrations of our Lyapunov agent versus Lagrangian, where we can see that the Lyapunov agent can control the cheater in a more stable way. Next, there are also these indoor robot navigation domain that we use for a proof of concept of our safe RL methods. Here, the main objective is to control the robot to navigate from start to go accurately, and of course to avoid ramming into obstacles such as furniture or humans. Here, for obstacle avoidance, instead of distance to objects cost, we do consider the constraints based on total energy on collisions. The main reason is we can allow the robot to touch but not collide into objects. Here, the states of the robot are the noisy LiDAR signals, and the policy outputs actions to control the motor motors. This is a video demonstrations of how our fetch robot navigates in the Google Office setting. You can definitely see that our robot can balance between accurately navigating from start to go while with a low collision energy. In conclusion, we presented two Lyapunov safe RL algorithms for continuous control, which is based on constraint policy gradient and also the embed safety layer. We demonstrate the effectiveness of these algorithms on benchmark MuJoCo tasks as well as an indoor robot navigation application. This is the end of our presentation. For more questions, please let us know in the online session. Thank you.